All right. We love to highlight student research, and I'm thrilled to have our final presentation today come from Rohan Yadav, a third-year computer science Ph.D. student here at Stanford University. He's generally interested in programming languages and computer systems with a focus in systems for parallel and distributed computing. In his presentation, Legate Sparse, Distributed and Accelerated Sparse Computing in Python, he will introduce Legate Sparse, a system that transparently distributes sparse matrix-based scipy programs across clusters of CPUs and GPUs. He'll discuss the design of Legate Sparse and show its performance on up to 192 GPUs of the Summit supercomputer. Rohan, welcome to the conference. Happy to have you here. Currently on mute.
All right, there we go. Yeah, thanks for having me. So thanks for the introduction. So yeah, I'm Rohan. I'm a third-year PhD student at Stanford. I work with Alex Aiken and Fred Kilstead, and I'll be talking to you today about Legate Sparse. So this is a way to kind of execute familiar scipy and NumPy-based Python programs across clusters of CPUs and GPUs. And so this is work in collaboration with a lot of folks over at NVIDIA as well. All right. So I'll get started. So to just, just to put everyone on the same foot, I just want to talk a bit about, the existing NumPy and scipy libraries and a bit about how people use them in practice. So, NumPy is a foundational library for array-based computing in Python. It's a nice abstraction over physical memory locations, and there's a huge number of APIs that NumPy has to sort of create and manipulate these arrays. Because of that, NumPy has been heavily used in the scipy system, which is this giant library for scientific computing. And it's got a whole bunch of APIs that are really useful in, of course, scientific computing, data science, machine learning, and more. And NumPy arrays are sort of the core building block of this library. And in particular, we're going to focus today on the portion of this library, the sparse module, which gives you ability to represent and do operations on sparse matrix data structures. And so at a very high level, some of the code you can write using some of these libraries, I have a bit of snippet up here. You don't have to look at all the details, but what it does is that it's gonna solve the heat equation on a 2D mesh, and it's gonna do this by using NumPy to construct a sparse matrix out of some diagonals, and then use scipy.sparse's conjugate gradient solver in order to actually do an iterative solve over this matrix. And the things to notice here, right? This code is maybe 10 to 12 lines of code, and you can express this very complicated kind of problem that we're trying to solve in all very high level, very Python notation. And so because of the popularity of these systems, people have always been looking at how to make this code go faster. People really like to write this code. And so, how can we make it really go faster? And so there's been a lot of work on accelerating NumPy and scipy. Particular, people want to just change this import statement. You want to say, instead of import NumPy, maybe you import something else as NumPy, and it's going to just run your code faster. And some of these systems out here are things like CuPy or JAX, where you can say import CuPy as NP, and your code will suddenly run accelerated on a single GPU. And sort of everything will just work and run a bunch faster if everything works out. And so this is great. And some of these systems also have like accelerated replacements of scipy.sparse too. So you can have your sparse matrix codes accelerated on that GPU as well. As your problem size gets bigger and bigger, perhaps you can't fit the data that you're actually trying to analyze on a single GPU. You want to start running on multiple GPUs or multiple nodes worth of resources. And so there has also been some work about distributing NumPy, in particular the cuNumeric project out of NVIDIA that I'll talk about a bit later, as well as the NumS project out of Berkeley and the DAS project, where you can take this NumPy import and you can replace it with something else like import cuNumeric as NP, and your NumPy code will start executing across distributed machines. However, there's no such thing out there for scipy.sparse. So you get that like at the current state of the world, you can write your dense NumPy programs across these clusters of GPUs, but if you want to represent sparse matrices, which come up all the time in scientific computing and machine learning, you're sort of out of luck. And so this talk is going to be about how we can build something, this separate kind of standalone sparse library that can interoperate with distributed NumPy replacements to give you that power of having both dense and sparse array programming across distributed machines in pure Python, right? So Legate Sparse is going to be this library for you, and you note that you sort of just change the imports of your NumPy program from cuNumeric and cuNumeric and Legate Sparse instead of NumPy and scipy. And we're going to have this, we're going to automatically take this program and scale it across a distributed machine for you. And the key point to note, I think, with Legate Sparse is that it's going to completely interoperate with Q-numeric. You don't need to worry about unnecessary synchronization or data movement when you cross these library boundaries. So you can note here that we're taking these distributed arrays created by Q-numeric and passing them directly into the sparse library. And that's sort of a very seamless thing, just like you'd expect from standard Python code. All right. So to give you a sense of the power of this system here, I want to show a bit of performance results early. So I have the same code on the left, and on the right, I have a weak scaling log plot of this code running out to 192 GPUs of Summit. So the way to read this plot is it's measuring weak scaling, meaning that we start with a problem size on one GPU out here, on one GPU out here. And basically, as we go from one GPU out to multiple GPUs, we're going to increase the problem size proportionally to the number of GPUs. So on 3 GPUs, we're running a problem size that's 3 times bigger than the one on one GPU. And so here we're comparing against CuPy and scipy, as well as the industry standard PETC library for running sparse matrix codes. And we can see out here, as we scale out to 6 GPUs or 2 CPU sockets, so a full node of Summit, we saw a pretty competitive performance with PETC, and we significantly outperformed the single-threaded scipy implementation of scipy.sparse. And out here now at 12 GPUs or 4 sockets, we're even crossing the network. So we're talking over InfiniBand now. Again, no code changes and great performance. And even out here at 32 full nodes of the Summit supercomputer, we have pretty competitive performance with PETC, again, from pure Python. So just to give a full overview of what Legate Sparse actually supports, so we're going to support several common sparse matrix formats that you're interested in, like CSR, CSC, etc. A variety of arithmetic and linear algebra operations on top of this library, on top of these formats. And then we're going to support a bunch of parallel format conversion and sparse matrix construction utilities as well. These things can't really be purely sequential if you want to scale to large machines. So of course, we have to include these as well. And finally, as we're getting closer and closer to covering more of scipy, we have a bunch of higher level things like iterative solvers and Runge-Kutta integration, eigenvalue estimation, and more kind of all packaged into the library itself. And we've been using it to develop some HPC and machine learning applications, and we're very interested in talking to new users. So if you have code out there that you think you're running it in scipy, it's a bit too slow right now, or you want to target some large data sets, please get in touch with us and check out the project and see how we can help each other. So that was a bit about the end of the ad pitch for it. But I want to talk now about how does this all work? Get into some of the details there. And I think when talking about how it works, I think that there's a couple of things that I want to touch on. And so the first important thing is this idea of how we actually can interoperate with Q-numeric. You notice we can just take these NumPy arrays and pass them straight to our library. Like, how do the two separate libraries actually agree on these different distributed data representations? Next, we actually have some distributed sparse matrix kernels, like this transformation from diagonal to CSR. And then we have these higher order, this full conjugate gradient solver. Like, how do we actually write all these without spending too much time reinventing the wheel and reinventing all of scipy? So while I talk about how the implementation works, I want to also set the stage with the kind of key things that were in our head about when we're implementing the library, what we want. And these key requirements are going to guide the decisions we make in our implementation. So hopefully it can give you a bit of a mental framework for what we were thinking about. So the first one is that we want to get scalable and portable performance without any code changes. And so really what that means is we want you to be able to run pure NumPy and scipy programs unchanged at scale. And we think that this is super important because we think a lot of developers out there don't have the expertise to really develop explicitly parallel MPI distributed codes that actually target GPUs and CPUs. And so by really sticking with the pure NumPy and scipy approach, we ensure that everybody can actually take advantage of the large machines, regardless of their expertise in programming these complicated machines. So that was a non-negotiable constraint for us. Second, we wanted to, of course, make sure that you can seamlessly compose with Q-numeric. The goal here is that you have something that mirrors the NumPy and scipy setup. And finally, the constraint that is a bit more nebulous, that doesn't show up exactly in the external view of the library, was that we want to have a maintainable implementation. And that's going to come up in two particular aspects. The first being that we want to make sure that the implementations of Legate Sparse and Q-numeric are not like really intertwined with each other. We don't want these two libraries to have to consider all the possible ways that they could interact, as that's going to sort of lead to an untangled mess of code in the background. And finally, sparse, if you program some sparse matrix operations, you'll know that these things require a lot of specialized code. And it's often there's a large number of variants you may need to write, like for all the different data structures, et cetera. So we don't want to be writing too much stuff by hand. We want to keep that, we want to avoid the amount of man hours going into developing this library. So given these implementation requirements, I want to now dive into the architecture of Legate Sparse and talk about how the different components of that architecture are going to help us achieve these goals. So a bit of an overview of the architecture. So we're going to build, so this whole system is built on a low-level tasking system, runtime system called Legion. And so Legion is a task-based runtime system that allows you to divide your computation up into things called tasks and help you distribute them across a machine. So it's actually going to be the vehicle for which we actually write and execute our code across clusters of GPUs. Legion is a very low-level C++ tasking-based API, and so we have this middle layer on top of it called Legate Core, which is going to be a friendly Pythonic version of that low-level interface that both Legate Sparse and Q-numeric are built on top of. So Legate Sparse and Q-numeric are going to talk to this middleware layer, Legate Core, which then is going to actually end up making the final operations down to Legion. So given these three requirements we had before, sorry, they're in a slightly different order than on the previous slide, but the idea, thinking about how to get scalable performance without code changes and getting good composability with Q-numeric, those two things are going to come out of how we design this middleware layer, Legate Core, and also how we actually utilize and leverage Legion. And then this idea of having a maintainable implementation is something that's going to cut across all of the different layers of the software stack here. So I'll talk a bit about how each of these systems make a conscious effort towards making that happen. So the first component of the system I want to talk about is Legion. And so, of course, as I mentioned, this whole system is implemented by translating from these high levels NumPy and scipy APIs down to ASCII task launch operations in the Legion runtime system. So the way this works is kind of all the operations that you launch in NumPy and scipy are going to translate down to a series of Legion tasks that are issued. For example, say your program does a sparse matrix vector multiply that may launch one or more tasks. Then you go into NumPy and use that data and perform a sort on it. That'll launch some more tasks, and so on and so forth. Legion is going to see this stream of tasks that are being issued, and it's going to compute a dependence graph on these tasks. So what that means is that some of these tasks are going to depend on others, and others can be independent of each other. So Legion will figure out what tasks depend on each other and which ones can run in parallel. Using this dependence graph that it computes, it's going to dispatch these tasks onto actual processors in your machine. So for example, it may decide that some of them should go on the CPU, some of them should go on the GPU. And then what Legion is going to do is it's going to insert the necessary data movement needed and the data movement and synchronization needed to ensure correct execution based on this dependence graph that it computed. For example, if you have a task running on some GPU and it produces some data needed by a task on a different GPU, Legion will issue that copy across those GPUs to make sure your data stays up to date. And so this is really good for talking about how we can get composability across library boundaries, because both Legate Sparse and Q-numeric are talking to the Legion runtime system directly. So these tasks that are launched by the different libraries are going to get synchronized and have the data flow between those libraries sort of as precisely as needed that is computed by the Legion runtime system. So to give an idea about what abstractions we're actually targeting here and what that programming model looks like, I just want to talk a bit about the Legion data model, and this will be sort of what is targeted by higher level operations in our system. So the core data structure in Legion is something called a region, which you can think of as basically just an n-dimensional array. And so, the NumPy arrays in Q-numeric are going to map directly down to these regions. And these sparse matrices in Legate Sparse are going to just map to packs of these regions. For example, normally you would represent, say, a CSR matrix with 3 arrays storing different kinds of metadata. We want to just store 3 regions directly distributed across our machine. And the way of expressing parallelism in Legion is this notion of a partition. And a partition is basically just chopping up your region into some set of subsets of that region. For example, here I've chopped up this matrix here into 4 pieces. And so this is a partition, a row-wise partition of that matrix. Then to talk about the actual computation you want to do, Legion lets you have tasks. And tasks are basically arbitrary pieces of code. In our work, we have C++ code for single-threaded CPU tasks, OpenMP code for multi-threaded tasks, and CUDA code to run on GPUs. And what Legion does is you're going to launch tasks on different subregions of your data. So I might launch a task on the red slice of this region that I have here and the green slice. And Legion can figure out that, hey, okay, these two regions don't intersect at all. So I can run these two things in parallel. And perhaps if I launch another task on the red region, I know where to move it to a different processor later in the system. So our system is going to basically operate by mapping data down to these regions and partitions and launching tasks corresponding to the computations we need to do on those particular regions. And so that sort of thing is going to be managed by the Legate core. And I'll talk about the key abstraction the Legate core provides now. So the problem of efficient library composition is going to come down to how these tasks actually choose the particular partitions of data that they operate on. That's sort of the most important thing. And you can consider this problem here, where suppose library A, like Legate Sparse, has a matrix, and it's going to decide to launch some tasks on this matrix, and it decides to use a row-wise partition of that matrix. But then we have a follow-up task launched by Q-numeric, say, that also is going to operate on that same matrix, but it decides to use a column major partition of that matrix. If the libraries don't agree on these partitionings, we're going to have to sort of do an all-to-all transpose to shuffle that data across the machine. So ideally, we want these two libraries to agree on these partitions. So ideally, that both those tasks should have used that same row-wise partition of the matrix, keeping the data at rest in the system. And the way that Legate core helps negotiate this is to have this way of defining tasks that is both composable and maintainable. And the idea here is to use something called constraint-based parallelism to share partitions across library boundaries. And so what I mean by that is that when you decide to launch a task, rather than specifying exactly like, hey, this task must use a row-based partition, what you're going to say is that this task is going to have certain constraints on how the arrays it uses can be chopped up. And Legate core is going to use something called a constraint solver to figure out partitions of the data that exist already in the machine that satisfy those constraints, allowing you to keep the data in place and have different libraries coordinate on those same partitions of data. So an example of this for really simple tasks inside Q-numeric is suppose you have a task that's going to add two arrays together. It's going to have an output array A and two input arrays B and C. Like the constraint you would add to this particular task is that A, B, and C need to be aligned. So that just means that I don't really care how A, B, and C are partitioned, but all I know is that those three partitions of the arrays should all sort of line up together. And what this allows us to compactly encode sort of all possible partitionings that A, B, and C could have. A can be, C could be partitioned row-wise, column-wise, and tiles. All of that is expressed through here and allows the system to choose a partitioning that sort of works for, works based on how the data already lives in your machine. This kind of thing scales to even more complicated tasks. For example, we have this CSR, this SPMV here. The particular details don't matter, but these constraints allow us to express pretty complicated things like aligning only some arrays in our system, and also describing relationships like data-dependent relationships between particular arrays. So this idea of having constraint-based parallelism is going to be key to composing parallelism across these library boundaries and actually having this seamless composition when you pass data from one library to the other. All right. So now the last bit of the system that I want to talk about is actually how we actually implemented much of Legate Sparse itself. And the key problem there that I want to talk about is this idea that there are too many sparse tensor kernels to actually implement by hand, and this becomes really complicated in a distributed setting as well. And so you have so many different data formats that scipy supports. You have so many different operations that it has as well, like matrix vector multiplication, matrix multiplication, adding matrices. And then you also have so many different hardware backends to target. You want to be able to target single-threaded CPUs, multi-threaded CPUs, GPUs. And the Cartesian combination of all these things is sort of just too much stuff to implement by hand. If you try and do this by hand, you'll probably only be able to optimize some small subset of these, and you won't be able to really get that full, wholly optimized system you may want. And the way that we get around this is to actually leverage recent developments in compilation technology. In particular, this compiler called Distal, which is something that also came out of our group. And what Distal does is Distal is a sparse tensor algebra compiler that targets distributed machines, meaning you feed it information about what computation you want to perform, and it's going to spit you out a bunch of code that actually implements that efficiently on a distributed machine. And at a very high level, what Distal does is it allows you to specify what you want to compute in some Einstein summation-like notation. Lets you specify how the data is compressed. The particular notation doesn't matter here, but for this matrix vector multiply here, you may specify that the input vectors x and y are dense, while a is a CSR. And then you also be able to specify what algorithm you want to use to distribute it across the machine. So for example, this particular snippet is going to use a row-wise distribution of that of the multiplication. And you can also specify to Distal how your data exists distributed across the machine. And putting all these together, Distal is going to output you code that runs efficiently on a supercomputer. And so how we utilize Distal is we take all these operations in scipy and these different data formats and ahead of time use it to generate a huge variety of kernels. We automatically generate a large portion of the library, and we get sort of all of that by optimized well, done automatically by this compiler, which really accelerated the development of the library. For the non-tensor algebra operations, there's kind of two buckets of them. I think the first one is kind of these auxiliary operations that don't really fit in any particular domain, such as just finding the diagonal of a matrix or maybe the min of some columns or something. So these we sort of unfortunately have to hand implement. It's a bit painstaking to do these, but there aren't too many of them. But what's really cool is all of the high-level operations, such as different format conversions, solves, and integrations, we can sort of get for free from the scipy implementation. And what I mean by that is if you go and look at the scipy code, their source code, a lot of the stuff is just implemented by using NumPy arrays. And so because we've worked so hard to integrate with cuNumeric and make sure that we can just ingest cuNumeric arrays and utilize them, we can sort of just look at the scipy library and get implementations of so many higher order kernels just for free, like the CG solve, the integrators, et cetera, which is kind of a testament to the benefit of working with no code changes and really focusing on compatibility. So that's going to conclude kind of the implementation and the design of Legate Sparse. And I want to talk a bit about just performance to show off what we can do. And so all of our experiments here can be performed on the Summit supercomputer, and we're going to compare against scipy, CuPy, and PETSy, which is both like scipy and CuPy. CuPy is this distributed, the single GPU implementation of scipy and NumPy, and PETSy is like a linear, the industry standard sparse linear algebra system. So the goal here of this performance comparison is to show you that Legate Sparse can have comparable performance to these single node or single GPU systems. And then you can take that same code and have reasonable weak scaling up to larger and larger machines. And we have applications from the scientific computing domain and machine learning domain. And we actually have some really complicated applications. They range from around 10 lines of code to over 1,000 lines of code, which some real applications just all written in pure NumPy and scipy that our system can handle. And so the first benchmark I'll show you, of course, is the same conjugate gradient solver we saw before. And I don't want to point out a couple more of the details this time than the first time I showed it to you. In particular, that we're going to have nearly identical performance to CuPy on a single GPU and have slightly worse performance than PETSy on all the GPU counts as we scale out. We're going to have nearly identical performance to PETSy on CPUs. And note that we significantly outperform the scipy system, which can't take advantage of multiple threads, let alone multiple sockets on a particular machine. And the next benchmark I can consider is a geometric multigrid solver. So this is a preconditioned CG solver that's going to use a multigrid approach to actually doing the solve. So it's going to take that input system of linear equations you have, and it's going to sort of coarsen that grid down into smaller and smaller versions and use those smaller versions to guide the search for the solution that's going on. So multi-grid solvers are known to be pretty tricky to implement in practice. And so the fact we can do this in pure Python is pretty nice. And so the results here overall similar that we're going to heavily outperform heavily outperform scipy. We have pretty competitive performance to CuPy. We're going to have pretty good performance out to around 24 GPUs, though we start to fall off a bit after that, which are some issues that we're looking to. We could definitely do better, but still it's pretty great to be able to scale this code out to several nodes of Summit. The final HPC style benchmark I have here is this is our most complicated application. This is around 1,000 lines of code. So this is a quantum simulation of the Rydberg equations that is meant to solve the maximum independent set problem, in case you are familiar with quantum computing. I am not that much. And the very core of this method is an 8th order Runge-Kutta integration. And so this particular application, it doesn't scale that well. We've isolated most of the issues to be the actual communication patterns inside the application, as it kind of is going to do an all-to-all communication at each step of the algorithm. But it's one of these things that the scientists we're working with had some code that really didn't really run very fast with scipy. We're able to take that code and sort of run it out to really large scales, which is for the quantum people really great, because the more memory they have, the bigger sort of system they can simulate. It's one of those things that the bigger you can get, the better it is for them. So that was really great. And finally, we have a little benchmark from the machine learning community, where we do a sparse matrix factorization problem on the movie lens data set. And the trend of results basically is similar as before, where for small data sets, you can utilize CuPy to fit on a single GPU and get pretty great performance. But as you start scaling up, eventually you're going to hit a point where CuPy is going to run out of memory. And then using Legate Sparse, you can sort of just keep scaling your code to more and more GPUs and keep running on larger data sets instead of having to try to rewrite your code or move to a different system. So that's going to end the results, and I sort of want to start to conclude here. And I want to leave with a couple high-level notes about the work we've done. And so, Legate Sparse is going to be this distributed and accelerated replacement for scipy.sparse. And we're going to combine several new technologies together to get composability, and as composability with like the numeric, this external distributed NumPy replacement. And we're going to have also an implementation that is sort of not all linked together. It's very actually separable. And finally, I've shown that you can achieve performance competitive with hand-tuned systems just writing pure Python code. So I've included my contact information here as well as down a link to the project. And so if you're interested, you have some code you want to accelerate, please reach out. So that's going to conclude my talk, and I'm happy to take questions. I see there were some in the chat. I'm sorry for not responding earlier. So let me try and, or no, okay, never mind. So I see Axel has raised his hand. Hey.
Yeah, so first of all, thanks for doing this. I think this is very useful because, believe me, the distribution of tasks is a royal pain in the behind. So, I think it's a great approach to do that, take that. I don't think I understood exactly how far you get the granularity. Because, ultimately, it depends on the ability of a system to distribute all of the tasks out to as many either cores, be it CPU or accelerator cores, as there are as possible. That's part one. And of course, the second thing is you always got to figure out what's the dependence between the data that you have. So I didn't quite understand how far that would go down if you do that on a per instruction basis, or if you do it on
it's not on a per instruction basis, but it's more on it's per. So we launched tasks for each operation in NumPy or scipy. So when you say like NumPy ... between a sparse matrix and like a vector, that thing turns into a series of tasks and describes, what data it uses.
Okay, so I see. So you're taking a relatively high-level language approach to all of it and say, we are taking a large chunk of this API, this library, and we distribute and farm it out. Is that correct?
Yeah, exactly. Okay. So by parallelizing and distributing the high-level operations, we can then also effectively map those down to accelerators and other things too, rather than like low-level heaps and things.
Okay, I get it. And then the other thing, and there's just a comment, has nothing to do with what you did, but I'm not quite sure I understand the affinity of everybody for sparse matrices, because I've shown it for over 15 years that a test for 0 or 1 takes longer than just brute forcing a multiply with 0 or 1. It takes, in fact, even less energy. Right. So I'm not quite sure why there's such a focus on sparse matrices, because again, brute force is just faster.
So the big focus is so computing on dense matrices is often much faster, but what the big benefit is for memory usage. So for many problems where you have a matrix where most of the entries are 0, perhaps that 99% or 99.9% of these entries are 0, you can represent problems you could never represent in the dense setting by storing it as a sparse matrix. So for example, for the common kind of matrices that show up in linear solvers, right? You can represent a huge matrix and sparsely, but you wouldn't be able to represent that at all in a dense setting.
Okay, I see. So your assumption is that the matrix is in memory and not in the accelerator, because by the time it's in the accelerator, I can guarantee you, I can even show you cycle counts. It's vastly faster to just brute force it, multiply by 0 or 1 than testing for 0 or 1.
Yeah, so I mean, even then, your data, it has to fit in the accelerator memory. So even then, like, it matters even more. Like the smaller your memory, the more important it is that you actually use the compact data encoding than something dense. Yeah.
Anyway, we can discuss this later, but offline. But yes, I think in general, great approach, great presentation, and certainly something that's needed.
Thank you.
Thank you, Axel, for that question. I currently don't have any other questions for you, Rohan.
Yeah, great. Well,
Steve, do you happen to have a question for Rohan, by chance?
No questions here.
Ah, Steve's really easy today. All
Yeah.
right. Fantastic. Well, thank you, Ron. I really appreciate the presentation. It's a great way to end day 2.
Yep.
So appreciate
Thanks for
that.
having me. And it was great to talk to everyone. So thank you.
Thank you.